Debugging is an essential aspect of GPU programming as it allows us to identify the source of any unexpected results or runtime crashes. To accomplish this, ROCm provides ROCgdb. ROCgdb is built on top of the GDB by adding ROCm-specific extensions that enables GPU program debugging. Since ROCgdb is derived from GDB, using ROCgdb is very similar to using the regular GDB. By using the ROCgdb debugger, we can effectively control GPU's execution flow, examine execution status, and compare with expected execution results. In this section, we will explore the capabilities of the ROCgdb debugger and learn how to use it for effective debugging. Before debugging any GPU kernel, we must compile the program using the -g flag so that the debug information will be included in the output binary. For example, we can run hipcc-g vic-add.cpp-o vic-add, which generates the binary vic-add with the debugging information. Now we are ready to debug with ROCgdb. Note that -g should not be added in release version of the software binary as it may slow down execution and leak proprietary source code. Let's initiate the debugging session by executing the command ROCgdb vic-add to launch ROCgdb. This will provide access to the GDB environment, allowing us to manage the program execution through the command line interface. It's important to keep in mind that if our program needs any arguments, we can send them to the debugger by utilizing the ROCgdb-args program command along with the arguments. This enables us to debug the program accurately with the required input parameters. For instance, we have taken 1, 2, and 3 as the input parameters in this example. In order to debug and comprehend the functioning of our code, setting up breakpoints is an essential feature offered by ROCgdb. It enables us to analyze the program's behavior until a specific point and investigate any unexpected execution results. The program will automatically halt at the configured breakpoints, allowing us to scrutinize variable values during execution. By comparing actual variable values with expected values, we can determine if the program is operating as intended. While standard GDB only permits setting breakpoints in the host program, ROCgdb enables us to set breakpoints in GPU kernels as well. Setting a breakpoint in the ROCm debugger is similar to using GDB. The command b, which is short for break, is used followed by the file name and line number where the breakpoint should be placed. There may be alternative commands to achieve the same objective in GDB or ROCgdb. In this example, we placed breakpoints at lines 17, 18, 57, and 67 of the vic-add program to analyze the code's behavior at those specific points. It's important to keep in mind that when using a debugger to set a breakpoint in GPU kernel code that isn't currently loaded, the necessary information may not be available immediately. This can happen when a GPU kernel has yet to be loaded. In such cases, the debugger will usually prompt you to make the breakpoint pending for future loads. If you choose to do so, the debugger will remember your breakpoint and try to set it when the relevant code is loaded. This explains why the breakpoint may appear as pending at first. By setting up multiple breakpoints, we can analyze the program's state at each breakpoint and gain insights into its logic. Once the breakpoints are in place, we can use the info-b command in GDB's command line interface to check them all. In the attached screenshot, we provide an example of multiple breakpoints set up in the vic-add program, and the info-b command is used to display them. It's important to note that the breakpoints for the lines of code in the GPU kernel code are initially pending as previously mentioned. However, after running the program and loading the kernel code, ROCgdb is able to successfully set the breakpoint. When we inquire about the breakpoint with info-b, it displays as set without any pending status. To start debugging in ROCgdb, one can use the R command. This command will run the program with the designated breakpoints and pause execution at the first one. After reaching a breakpoint, the C command enables us to resume the program's execution from the current breakpoint. Upon using this command, the debugger will execute the program until it hits the next breakpoint. where it will halt the execution once more. This feature is helpful for analyzing the program's behavior at different stages by stepping through it. One line of the source code can have breakpoints set, but multiple threads can execute it. To examine program values more thoroughly, it's necessary to understand which threads are running in the system and which one is currently active. The info threads command can help achieve this goal. When used in ROCgdb, it provides information about the threads running in the program. Here we only show 27 of all the currently running threads due to space limitations, but users can check all the threads by moving to the next page of the display. In the first 27 threads, we see 2 CPU threads, 1 and 2. The rest 25 are GPU threads. Here we have to point out that a GPU thread in ROCgdb is actually a wavefront denoted by AMD GPU wave. These wavefronts are identified by the lightweight process numbers such as 2:1:1:1. However, a more useful identifier is the index of the block and the wavefronts, following the lightweight process ID. For example, we see that 500/3 is the third wavefront in the block with an X index of 5. The two zeros are Y and Z indices of the block, but since we launched a one-dimensional kernel, they are both 0. Finally, ROCgdb uses a star sign to represent the current thread. Later, as we examine the code and register values, they belong to the highlighted wavefront. Next, we need to check what code that is currently executing around the brick. For CPU, we probably want to use the L or the list command to check the source code. It still applies to GPU programs. However, since the GPU binary is optimized, it may not be easy to link a line of code with the assembly or to link a variable with a register. Therefore, GPU debugging is usually done at the assembly level. If the audience is not familiar with the AMD GPU assembly, please refer to our Unit 5 for a detailed information. To check assembly code, we can use the disassemble command. The output of the command disassemble gives a series of assembly code. The assembly code consists of a list of instructions, each identified by a memory address. The first column shows the memory address of each instruction followed by the instruction itself. The fat arrow symbol indicates the currently executing instruction. The instructions themselves perform a series of operations on registers. To debug, the key is to find if the register values are within our expectations. So the next step is to check the register values. The info register command in ROCgdb mode is used to display the current values of all the registers. This can be useful for debugging purposes as it allows you to inspect the current state of the registers at any point during program execution. When you run the command info register in ROCgdb mode, the debugger will display a list of all the available registers and their current values. Note that the info register command will only display the values of the registers that are currently in the use by the program. If the program has not yet initialized or used a particular register, it may not be displayed in the output of the command. Additionally, the availability of GPU registers may depend on the specific GPU architecture being used. Here in this example, we see a list of vector registers that start with V, accumulator registers that start with A, and scalar registers that start with S. There are also specialized registers such as MO, PC, exec, and VCC. For vector and accumulator registers, we can see that they may have different values for different threads. In our case, only VO has non-zero values. In general, a programmer may want to examine the register values, execute some extra code, and check how the register values change. By repeating this process and comparing the values with their expectations, software bugs can be found. We believe the command we introduced in this video is sufficient for the GPU programmers to identify most of the bugs. Therefore, in the next video, we are going to start talking about profilers.